Hi, Assalamualaikum students. This is tutorial 02, in which in this video I'm going to cover tutorial for chapter 1.3. Question number 1. A piston cylinder device initially contains 0.07 meter cube of nitrogen gas at 130 kilopascal and 120 degrees C. The nitrogen is now expanded polytropically to a state of 100 kilopascal and 100 degrees C. Determine the boundary work in kilojoule done during this process. For this question, we know that the nitrogen inside the piston cylinder is expanded polytropically, in which the process happen here is polytropic. From state 1, pressure is 130 kilopascal and the temperature is 120 degrees C. But at state 1, the volume is 0.07 meter cube. So from this state 1, it is expanded polytropically into state 2, which is pressure is 100 kilopascal, temperature is 100 degrees C. So we need to find the boundary work. Because of this is polytropic, the equation that we can use is V2 minus P1 V1 over 1 minus N. So if we look at the given information here, we can see here, other than the polytropic index, which is not given, the V2 is not. So we need to find first the V2, then after that we have to find the N. First, how can we find the V2? Is by using the ideal gas equation, which is V2 is equal to mRT2 P2. But for entire system, we still don't know what is the mass. So means that we need to find the mass first before we can find the V2. So mass we can also find by using ideal gas equation, which is M is equal to M1 V1 over RT1. So mass will not change. How many states that we have, the mass will not change. The only change is the volume. So mass we can find by using info from state 1. So P1 is 130 kilopascal, V1 is 0.07 cube over R. Because of this is nitrogen gas, so we take R for nitrogen gas, which is 0.2968 kilojoule per kg Kelvin, which is we can get from table A1, and T1 is in Kelvin, which is 393 Kelvin. Then mass you will get 0.07802 kilogram. So from this mass we can substitute inside here. So V2 we will get 0.07802, R is 0.2968, and T2 is 373.15 over P2 is 100 kilopascal. So we solve, then we will get 0.08637 meter cube. So this is V2. So from this V2 we can substitute inside here to get the WB. But before that, we still don't know the N. So how to find the N? Because of we already found the V2 and we have all the info for P1, V1 and P2 and also V2. So we can use this equation, which is P1 V1 to the power of N is equal to P2 V2 to the power of N. And now we need to find this N. So we substituted all the value inside this. P1 is 130 kilopascal, V1 is 0.07 to the power of N is equal to P2 is 100 kilopascal and V2 is, just now we have found 0.08637 power of n. So after we solve this, so we will get n is equal to 1.249. So once we get the n, so v2, this n we can substitute in this equation. So then we can solve this boundary work equation. After we have substituted all the value inside here, so we solve, then we will get the answer is 1.86 kilojoule. So that's how we solve question number 1. Next, question number 2. A mass of 5 kg of saturated water vapor at 300 kilopascal is heated at constant pressure until the temperature reaches 200 degrees C. Calculate the work in kilojoule done by Steve during this process. From the question, it is mentioned to you that we have 5 kg of saturated vapor, which is it will be heated until the temperature reaches 200 degrees C, but the process happened at constant pressure. So when it is constant pressure, the process is isobaric. So we need to find the work. So for this system, we can find through the boundary work. But this boundary work is according to the isobaric process. And we know that the equation for boundary work for isobaric process is equal to this equation. So this capital letter of V is volume and the small letter of V is specific volume. According to this equation, M is given and P is also given, in which M is equal to 5 kg and P is equal to 300 kilopascal. So it happened isobarically, so we can just use this pressure. Just that the V2 and also V1 we have to find. So it was mentioned in the question as well that the state 1, the phase is saturated vapor, in which the pressure is 300 kilopascal. For state 2, it is heated to temperature 200 degrees C and the pressure is still 300 kilopascal because of it is isobaric. So from here we need to find the V1 and also the V2. We need to find the boundary work, so we have to find the V at state 2 and also the V at state 1. We already know the phase, we just go directly to table A5. Then at pressure 300 kilopascal, we just find that the V1 is equal to Vg because of it is saturated vapor. So V1 is equal to Vg at 300 kilopascal. Just get the value, which is 0.60582 meter cube per kg. So this one is V1. We need to identify first what is the phase for state 2. So we go at table A4, then we check at temperature 200 degrees C and we have found that the given pressure here is lower than the P saturated. So means that according to the phase condition, the phase of state 2 is superheated. So we straight go to table A6, in which at table A6 you find at pressure 0.3 megapascal and T is 200 degrees C, and we can find that the volume is 0.71643 cube per kg. So now we have found the V1 and also the V2. Then we can straight away calculate the boundary work. So boundary work is equal to MP V2 minus V1. So it is equal to M is 5 kg, P is 300 kilopascal. So V2 is 0.71643 minus V1 is 0.6058. Then the answer we will get 165.9 kilojoule. So that's how we solve question number 2. Next, question number 3. A mass of 2.4 kg of air at 150 kilopascal and 12 degrees C is contained in a gas-tight frictionless piston cylinder device. the air is now compressed to a final pressure of 600 kilopascal. During the process, heat is transferred from the air such that the temperature inside the cylinder remains constant. Calculate the work input in kilojoule during this process. For this question, we can see the statement that even though the heat is transferred, but the temperature inside the cylinder remains constant, and because of the system can achieve the equilibrium by its own, so means that the system is applying the quasi-static process. So the condition here is quasi-static and it happens at constant temperature, which means isothermal. So we need to calculate the work input in which we can use the boundary work. We have to use the boundary work equation for isothermal process, which is mRT ln P1 over P2. Because of we are given with the pressure for both state P1 and also P2, so it is better we use this boundary work equation. So P1 given is 150 kilopascal, the P2 is 600 kilopascal. So the temperature is 12 degrees C and the mass is 2.4 kg. So all the values are given, so we can just straight away calculate the boundary work here. Then we substitute all the value inside this equation until we get this. So we can see here the M is 2.4 kg, the R, we took the value of R for air from table A1, temperature is 12 degrees C, and ln P1 is 150 and P2 is 600 kilopascal. Then we solve, then we will get negative 272 kilojoule. So the negative sign indicates the work is done on the system. Next, question number 4. A frictionless piston cylinder device contains 2 kg of nitrogen at 100 kilopascal and 300 Kelvin. Nitrogen is now compressed slowly according to the relation PV to the power of 1.4 is equal to constant until it reaches a final temperature of 360 Kelvin. Calculate the work input in kilojoule during this process. From the question, we can see the relation of PV to the power of 1.4 is equal to constant. I always mention to you, when you are given with this relation, means that that process is undergoing polytropic process. So for polytropic process, in order to find the work, we can find the work through this equation. We can see here there are two equations, which is using P and also temperature. Because of in the question given to you, there are T1 is equal to 300 Kelvin and T2 is equal to 360 Kelvin. M is also given, which is 2 kg, and because of most of the values can be fit into this equation, so we should use this equation. So boundary work we can get after we substitute all the values inside here. M is 2 kg. R, we will get the R for nitrogen from table A1, 0.2968. T2 minus T1 is 360 minus 300 over 1 minus N. So the N is 1.4 here. 1.4. So after we solve, we will get negative 89 kilojoule. And again, the negative sign indicates that work is done on the system. Next, question number 5. A piston cylinder device contains 0.15 kg of air initially at 2 megapascal and 350 degrees C. The air is first expanded isothermally to 500 kilopascal, then compressed polytropically with a polytropic exponent of 1.2 to the initial pressure, and finally compressed at the constant pressure to the initial state. Determine the boundary work for each process in kilojoule and the net work of the cycle in kilojoule. From the question, when we read carefully, we can see the A undergoes a cycle with 3 processes. So let us look one by one. State 1. The pressure is 2 megapascal. The temperature is 350 degrees C. So then the air is expanded isothermally. So means that it will go to state 2, in which it happened isothermally. So for state 2, we have the pressure is 500 kilopascal and the temperature is still 350 degrees C. So next, it is compressed polytropically. So means that it will go to state number 3. At this time, it happened polytropic. So at state 3, we know that the polytropic exponent is 1.2, and from this pressure, it will become to the initial pressure, which is P is equal to 2 megapascal. Then it finally compressed at constant pressure to the initial state. So it means that it will be back to state number 1, but at this time it happened at constant pressure, which is isobaric. So it will become the initial state back, which is 2 megapascal, and temperature is 350 degrees C. So we can see here there are 3 processes with state 1 until state 3 and back to state 1. So we need to find the boundary work 1 to 2 at isothermal process, WB2 to 3 polytropic process, and 3 to 1 at isobaric process. For 1 to 2, which is isothermal, we can use the equation P1 V1 ln V2 over V1. For 2 to 3, we can use the polytropic boundary work equation, which is P3 V3 minus P2 V2 over 1 minus N. For boundary work 3 to 1, we will use the boundary work for isobaric, which is P3 V1 minus V3. So lastly, we need to find the net work. So the net work, W net, is equal to V1 to 2 plus V2 to 3 plus WV 3 to 1. So you will get the W net and also the boundary work for each process. So now we have to find one by one the boundary work. First, we find the boundary work from 1 to 2 by using P1 V1 ln V2 over V1. So because from the question we are not given with any volume, so we need to find the volume first. We need to find the volume for state 1. So refer back to the state 1 just now. So we use all the info from state 1 to find the V1. And RT over P1, it is equal to M just now is 0.15 kg. R is 0.287 kilojoule per kg Kelvin. So you can find the R for air at table A1, and the temperature is, you take the temperature at state 1, which is 350 plus 273 Kelvin over P at state 1, which is 2000 kilopascal. So you will get 0.01341 meter cube. Next, we need to find the V2. We still use this equation, M R T2 P2. So M we can still use because M, the mass will not change. So 0.15, 0.287, and the T2 is still 350 Kelvin because of it is isothermal, right? 3 over, but this time P, we should take P from state 2, which is 500 kilopascal. So we will get 0.05364 meter cube. So after we get the V1 and also V2, we can proceed with this calculation in order to find the boundary work from 1 to 2. So boundary work from 1 to 2 is equal to the P1 just now is 2000 kilopascal. The V1 is 0.01341 ln V2 is 0.05364 over V1, which is 0.01341. So after we solve, then we will get the 37.18 kilojoule. So this is WB 122. Next, boundary work from 2 to 3, and this is polytropic, so we should find through P3 V3 minus P2 V2, 1 minus N, because just now we have found that the V2 is equal to 0.05364 meter cube. So in order to complete all the values inside here, so we need to find the V3, because P3 is given, only V3 we need to find. So how we can use this relation? So P2 is 500 kilopascal, V2 is 0.05364 to the power of 1.2. It is equal to P3 is given, which is 2000 kilopascal, just that we want to find the V3, so of 1.2. So after we solve, then we will get the V3 is equal to 0.01690 meter cube. So after we have found the V3, we can put inside here, so we can calculate the boundary work from 2 to 3, which is V3 is 0.01690 minus the P2 is 500 kilopascal, V2 is 0.05364 over 1 minus N. N is 1.2. Then we solve, then we will get negative 34.86 kilojoule. This is boundary work for 2 to 3. Next, we find the boundary work from 3 to 1, which is it is at constant pressure or isothermal, so we use this equation V3 V1 to V3. So just now we have already found V1 and we have also already found the V3. So the P3 we know it is initial state pressure, so we just substitute all. So P3 is 2000 kilopascal, V1 is 0.01341 just now, and V3 is 0.01690, and you will get negative 6.97 kilojoule. Just don't worry with the sign, because of the sign it represents either that process is compression or expansion. So for 3 to 1 it is compression, so that is why the work here is negative. Next, we have to find the network. So when we find the network, we have to do the summation of all boundary work for all the processes, which is from 1 to 2 plus 2 to 3 plus 3 to 1. So just now we take the value that we found just now, which is 37.18 plus negative 34.86 plus negative 6.97. So we will get the 4.65 kilojoule. So that is how we solve question number 5. So that's the last question for this video. I hope you can understand and it is useful for you. Till we meet again in the next tutorial video, I think that's all from me. Thank you and Assalamualaikum.